Check one, two, three. Can you all hear? Is it loud and clear? If so, put on the chat. Can you all hear? Is it loud and clear? Is it loud and clear? You can put in the chat now. Is it loud and clear? So I can put in the chat now if it's loud and clear. Whoever is joining can put in the chat. Okay, we'll start in another 5 minutes time. Huh? 5 minutes time. Right. Can you all hear me? Is it loud and clear? Okay, put in the chat. Loud and clear? Okay, great. Right. So I decided to have this particular session actually because we could what you call complete this very small section. Number one, tsunami wave. Next is laser, and then sonic boom. Yeah, laser and sonic boom. So these sections actually will be helpful for you, so that you can what you call quickly finish it off because these are very small sections. Majority are MCQ sections. Yeah, majority are MCQ sections. Right. So we'll start off with earthquakes. We talk about seismic waves, waves which occur due to the sudden tectonic movement. Right. So just to start off, carefully have a look at this. Now, look at the board carefully. Look at the board carefully. To take the earth is actually floating on lava or magma. So there is something called tectonic plates. What plates? Tectonic plates. Now these tectonic plates are actually very dynamic. So imagine a glass of water. Imagine a glass of water. On that glass of water, you have ice cube. On that glass of water, you have ice cube. Closely packed with each other. Closely packed like that. So you will see that this is what very dynamic. This will move up and down. So it's slowly moving, rubbing on each other. So therefore, it's a highly dynamic situation. Okay? Highly dynamic situation. So tectonic plates are also like that. So for example, if you take this as a tectonic plate, if you take this as a tectonic plate, this is magma or lava. This is magma or lava. So these tectonic plates are actually what floating on magma or lava. Here, tectonic plates are actually floating on magma or lava, right? So therefore, it is very clear. This is not at rest. This is always what dynamically moving. Clear? This is always dynamically moving. So even the plate that we are now, if you take Sri Lanka, now if you take India, if you take Sri Lanka, here we have something called the Indian plate. So we are actually on the Indian plate. Now some of you all might be asking, sir, can we see these plates? These plates are at the bottom of the ocean. So on top of these plates, if I draw it, these are your tectonic plates. Here lava, here you have water. Here only land. So these tectonic plates are moving dynamically on lava. Good. So the tectonic plates we can't see actually, but they are there at the bottom of the ocean. Is it clear? They are there at the bottom of the ocean. Understood? So right. So now you have a small idea about tectonic plates. I will show the videos in a while, but for now. So here you have lava. Here you have the tectonic plates. On top of that, you have seawater and then land. So technically, we are also dynamically. Now here you have water, land, everything is here. So when the lava has dynamic movement, the tectonic plates also are moving. Accordingly, the water and the land also is what changing. So we are in something called the Indian plate. Indian plate. And here near the Himalayas, you have the Russian plate. You have the Russian plate. Have you heard they say that what do you call every year Himalaya increases in height? Ah, Himalaya increases in height just because the Indian plate is pushing on the Russian plate. Imagine there is a carpet. You go to the edge of the carpet and you push it with your legs. What will happen? Small waves will form. No? Like that only. That means there is a small push causing what? This Himalayan ridge. So these mountains, whether it's here, the Himalaya, whether it's Rocky Mountains in America, all of that is caused because of a tectonic plate movement. So remember, the Earth and its dynamic nature is actually formed because of what? Earthquakes. Earthquakes and movement of tectonic plates. I'm sure if you're done geography, if you're done O-level geography, and maybe if you're done biology as well, those days there was only one huge continent called the Pangea. Have you heard about it? Then, as time went by, they broke off, and as the sea currents changed, they broke off, and then what we have now, what do you call, different continents, and still these continents keep on what changing. Now, if you heard, Africa, African continent is being broken somewhere here. There's a new plate being formed. These are things which you can go on YouTube and you can research. So these are new things which are already there. So remember, my whole idea is to tell you that tectonic plates is always dynamic, absolutely dynamic. Because of this dynamic nature, everything on the surface will what change. Mountains are formed, mountains are removed, ridges are formed. Now here in Africa, actually there is a big sinkhole being created here. So there's going to be a shift. So those things take place because of tectonic plate movement. Clear? Right. And a small sentence there. Take your note, write this. That's right. The earth is made up of many tectonic plates. The earth is made up of many tectonic plates. The earth is made up of many tectonic plates. These tectonic plates are floating on lava. These tectonic plates are floating on lava. These tectonic plates are floating on lava. Therefore, these plates will rub on each other. Therefore, these plates will rub on each other. Therefore, these plates will rub on each other, creating dynamic motion on the surface of the earth. Creating dynamic motion on the surface of the earth. Creating dynamic motion on the surface of the earth. Creating dynamic motion on the surface of the earth. This dynamic motion will create earthquake. This dynamic motion will create earthquake. And seismic wave. And seismic wave. Seismic wave. Okay? And seismic wave. Okay? Right. Look at this carefully. Look at this carefully. And a small sentence. We are in the Indian plate. We are on the Indian plate. We are on the Indian plate. And because of the dynamic motion of the Indian plate, and because the dynamic motion of the Indian plate, we can observe A change in height in the Himalayan hills. A change in height in the Himalayan hills. And the height keeps on increasing every year. And the height keeps on increasing every year. And the height keeps on increasing every year because the Indian plate is pushing on the Russian plate. The Indian plate is pushing on the Russian plate. The Indian plate is pushing on the Russian plate. Okay, no? Right. So this is your basic, what you call, introduction. Actually, if somebody asks you, why do we have earthquakes? That's because of what? Tectonic plate movement. Because the tectonic plate is moving only, we are getting what? Seismic wave. Without the tectonic plate movements, guaranteed there is no seismic wave. Okay, no? Right. Now look at this. Now earthquakes occur inside the earth, below the earth. This is called the focus. We call that the focus. Or some people also call it the hypocenter. What center? Hypocenter. Here, hypocenter. So here, hypocenter is there. Remember, if you project this point to the surface of the earth, so wherever the earthquake is taking place, if you project it towards the surface of the earth, the point on the earth is called epicenter. What center? Epicenter. Now those days when you have an earthquake, they say the epicenter is in Turkey. That means what? The surface is there in Turkey. Below that, somewhere in a depth only, earthquake has taken place. If they say epicenter is in Pakistan, yes, maybe surface is Pakistan. Hypocenter is exactly some depth below. Okay? So wherever the earthquake takes place, that is called the focus or the hypocenter. If you project the point to the surface of the earth, that is called what? Epicenter. Right? No? That's right. Wherever the earthquake takes place, we call that location the focus. We call that location the focus. We call that location the focus. Or the hypocenter. We call that location the focus or the hypocenter. And if we project that point to the surface of the earth, and if we project that point to the surface of the earth, and if we project that point to the surface of the earth, the point on the earth is called epicenter. The point on the earth is called epicenter. Clear? Quickly draw this. You can put on the chat now. Is it clear? Whatever you all learn, whatever you are hearing. Understood? Yes or no? Is it clear? Put it on the chat. Huh? Draw this down quickly. Right? Now, remember, if you take the earth, Outer surface is the crust. Outer surface here is the crust. Now, when you buy bread, what is the outer surface called? Crust. No? This is called the crust. Here you go, the crust. Then you have the mantle, not mental, mantle. And then you have the core. This is the core. Mantle. Remember, waves that are traveling on the surface are called surface waves. So waves which are traveling on the crust are called what? Surface waves. So waves which are traveling on the crust are called surface wave. We have two types of wave. One is called surface wave, and waves that go through the body. Body means it goes through the mantle, the rocks, the liquid, all of that. Waves that go through the body are called body wave. So how many types of seismic waves do you have? You have two types of seismic waves. One is called surface waves. The other is called what? Body waves. So what we'll do is we'll write this first. Body waves first, surface waves second. Okay, no? Let's write. When an earthquake takes place, when an earthquake takes place, there are mainly two types of wave. There are mainly two types of wave. There are mainly two types of wave. First one, write body waves. Huh? First one, body wave. First one, body wave. Second one, surface wave. Body waves, surface wave. Body waves, surface wave. Right. Now write subtopic, body wave. Now write subtopic, body wave. Right. Now what do you mean by body wave? A body wave is a wave that travels through what? The internal body or internal body of the earth. So travels through the body means from the mantle to the core to the other side. So a wave that travels from one end to the other end of the earth through the earth, that is called a body wave. Right there. A body wave, a body wave is a wave that travels through the earth. Is a wave that travels through the earth from one end to the other. Is a wave that travels through the one end to the other. Right. Now remember, when an earthquake takes place first, I'll draw it here. When an earthquake first takes place, let's say somewhere here you have the earthquake, here the epicenter, here you have the epicenter. This is called the, and to measure the earthquake, what do we have? To measure the earthquake, we use a device called the Richter scale. What scale? Richter scale. So Richter scale has a probe to the earth, inside the earth. And here you have a device. So this is called a Richter scale. Richter scale. Clear? And what happens is, when the earthquake takes place, the first wave that reaches the Richter scale is called the P wave. Now, what do you mean by P wave? Primary wave. So, primary wave is a body wave. So body wave, I told you there are two types. What are the two types? First type is going to be P wave. P wave is a primary wave. Primary wave. Remember, it is a longitudinal wave. It is a longitudinal wave. Now, why do you call it the P wave? Because it's the first wave that comes. It's the first wave that comes. First wave that is detected. That is detected. First wave that is detected is called the P wave. So in the Richter scale, the moment it goes up like this, that is your P wave. Remember, it is the fastest wave. Fastest wave. It can travel through solid, liquid, and also what? Gas. Solid, liquid, as well as gas. So primary waves can travel through solid, liquid, and gases, no problem at all. It is the fastest wave. It is a longitudinal wave. Okay? So the first wave that comes is called the primary wave. Let's say the velocity of the primary wave is Vp. We don't know the distance. Let's say this distance is simple d. Right. Then what happens? Then you have S wave, secondary wave, secondary wave. That is the wave that comes next after left. Can you see the primary wave has come? After a small gap, the secondary wave has come. So secondary wave is actually much more slower than. So I'll draw here. This is your S wave. Secondary wave is much more slower than primary wave. Secondary wave, it's a transverse wave. Transverse wave. They might ask this for MCQ. Transverse wave. It is slower than P wave. Slower than P wave. Slower than P wave. Look at the board now. Why is it slower? Why is it slower? Because remember, unlike primary wave, S waves don't travel through liquids and gases. S waves will travel only through what? Solid. So, only through solid. Only through solid. So, therefore, primary waves travels through solid, liquids, and gases. S waves will travel through only what? Solid. That is why it's slower. So, secondary wave has come. We'll take the velocity as Vn. So, understood? No? So, when an earthquake takes place, what's the first wave that comes? Quickly tell. Type in the chat. What's the first wave that comes? What's the first wave that comes? Very good. Primary wave. What is the second wave that comes? Secondary wave. Primary wave is transverse or longitudinal. Longitudinal. Secondary waves is transverse or longitudinal. Transverse. Is it clear? Transverse. So good. Let's try this then. Let's try this. Right. Let's try it. When an earthquake takes place, when an earthquake takes place, when an earthquake takes place, we can detect the earthquake using a Richter scale. We can detect the earthquake using a Richter scale. We can detect the earthquake using a Richter scale. Using a Richter scale. Keep writing. The first wave that reaches, the first wave that reaches the Richter scale. The first wave that reaches the Richter scale is known as a P wave or primary wave. Is known as a P wave or primary wave. Is known as a P wave or primary wave. Right. Under P waves, write this. P waves are longitudinal waves. First point. Longitudinal wave. Longitudinal wave. Next point. It is the fastest wave. It is the fastest wave. It is the fastest wave. Third one. It can travel through liquids, solids, and gases. 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 Next one. It is the first wave to be detected in a Richter scale. It is the first wave to be detected in a Richter scale. It is the first wave to be detected in the Richter scale. In the Richter scale. Okay. Right. Then the second one. S wave. S waves. Another try. This is also known as the secondary wave. This is also known as the secondary wave. This is also known as the secondary wave. Next point. It is the second wave that is detected in the Richter scale. It is the second wave that is detected in the Richter scale. It is the second wave that is detected in the Richter scale. Third point. It is a transverse wave. It is a transverse wave. It is a transverse wave. Next point. It is slower than the P wave. It is slower than the P wave. It is slower than the P wave. Next point. It travels only through solid. It travels only through solid. Right? So body waves have how many forms? Quickly tell. How many waves body waves have? How many types body waves have? Two types. What are the two types? Quickly. Type, huh? Primary waves, secondary waves. Clear? Primary waves, secondary waves. Okay. Right. So that is done. Now look at this. Like I said earlier, Richter scales are used to detect where the earthquake has taken place. There. Where the earthquake has taken place. Now look at this. Observe. Huh? So we don't know this detects. The Richter scale will detect there is an earthquake taking place. First wave that has come is your primary wave. Second waves are going to be your S wave. Now let's take the time gap. Time taken for primary, distance over Vp. Time taken for secondary, distance over Vs. Who will take a longer time? Secondary wave will take a longer time. Ts minus Tp is d over Vs minus d over Vp. Okay, no? d over Vs minus d over Vp. So secondary wave will take a longer time to come. So the time gap between the primary wave and the secondary wave, d 1 over Vs, 1 over Vp. This is the time gap between the primary wave and the secondary wave. Now using this, you can simplify the basic relationship. D is equal to Ts minus Tp divided by 1 over Vs minus 1 over Vp. 1 over Vs minus 1 over Vp. There you go. So if you know the time delay between the secondary wave and the primary wave, that you divide by this relationship, you can find the location where the earthquake has taken place. Now, if you take Sri Lanka, I'll give a simple example. In Sri Lanka, we have 3 earthquake detection locations. One is University of Peradeniya. I have been to that, what you call, seismic location. Next is Oluville. Oluville, Pothaville, that region. Next is Mihintale. So I have been to the seismic laboratory at Peradeniya, and I have been to the seismic laboratory at the University of Rajarata, Mihintale, because that's my university. So I have been to these 2 places. So they are separately, what do you call, blocked out. It's like a small room in the middle of what do you call the jungle, like a thing. There's a probe going inwards, and there's a what do you call Richter scale working. Now, whenever earthquake takes place, what happens is there is something called triangulation. Using triangulation, they can detect where the earthquake has taken place. Now, if you take, I'll draw this a bit bigger, broader like this. So here you have in Kandy, Central Hills, Oluville, Mihintale. So when an earthquake takes place, this will detect, this will detect, this will detect. Using something called triangulation, we can exactly find out which location or what place the earthquake has taken place. So triangulation means they will draw arc from here, arc from here, arc from here. Where all those 3 arcs meet, that is where the earthquake has taken place. So using the triangulation, now in our university, 3rd year, we had a what you call unit called seismology. If you do physics, there's a unit called seismology, oceanography. That means about the ocean, how waves occur, how the sea waves work. And then there's another unit called what? Seismography. So seismology. So you learn all of this there if you learn physics in detail. So using these 3 locations only, we can triangulate and find. There, we can triangulate and find. Now, in the Pacific, because majority of the earthquakes take place in the Pacific, there is a system called NOAA. You know NOAA, no? Not the biblical Noah, but it stands for that. So National Organization of Aquatic something, NOAA. Using these NOAA systems, they can find out where earthquakes take place, and they can have a pre idea whether the earthquake is coming or not, or when is it coming or not. So these are actually modern systems which are used, but we are not talking about them in your syllabus, unfortunately. But I just given you a small idea of actually the modern systems are. So this is the basic idea that you will need. By detecting the time gap between the primary and the secondary wave, we can find the location where the earthquake has taken. Is it clear? Understood? That's right. By detecting the time gap, between the primary wave and the secondary wave, by detecting the time gap between the primary wave and the secondary wave, reaching the Richter scale, we can find the location of the earthquake. We can find the location of the earthquake. We can find the location of the earthquake. We can find the location of the earthquake as indicated below. So you can draw this, quickly write it down. Okay, finished. Done. Quickly write down. So using the body waves, primary wave and secondary wave, we can exactly find out the location where the earthquake has taken place. Right, enough, no? Enough time, no? Quickly you can roll. Right. Now, primary wave, secondary wave will come and stop. Clear? Then comes the most destructive wave. Those are called what? Surface wave. Buildings fall. Railway tracks are crooked. Roads collapse. Huh? All of that. Cars fall into a hole. The road breaks in, you fall in. All of that occurs because of what? Surface wave. All of that occurs because of what? Surface wave. Is it clear? Right. Look at this carefully. Now, surface waves, there are two forms. Surface waves, there are two forms. Surface waves, there are two forms. One is called love wave. The other is called Rayleigh wave. One is called love wave, the other is called Rayleigh wave. Now, love wave means it's in remembrance of a scientist who found it. The vibrations or the shift will take place or the wave will travel what? Side to side. Like this. Vibrations are taking place side to side. Rayleigh waves, up and down, up and down, up and down. Now, side to side motion. Now, if you see a railway track, now normal railway track is straight, no, like this. Railway track is straight, no. After earthquake has taken place, the railway track is crooked like this. Railway track is crooked means guaranteed what? Love waves have passed through. Remember, the surface waves only cause a lot of damage to property and human life. Nothing else. Primary waves and secondary waves don't cause property and life damage. Surface waves will cause property and life damage. I'll show a video in a while. You can see it. Okay. So, love waves move side by side. Rayleigh waves move up and down. So, Rayleigh waves move up and down. Rayleigh waves move up and down. So, if you see a road or whatever, the road has gone like this, up and down, up and down, up and down. If the main carpet or the tar carpet has gone up and down like this, not in Sri Lanka anyway, it's like that, without even earthquakes. I'm just telling, going up and down, up and down, up and down after earthquake. That is because of what? Rayleigh wave. Right. Second one is surface waves. Let's say surface wave. Surface wave. Let's write let's write there are mainly two types of surface waves. They are Roman number 1, love wave. Roman number 1, love wave. Let's write love waves is the side by side movement. Love waves is the side by side movement or side by side vibration. Side by side movement or side by side vibration which takes place on the surface of the earth. Which takes place on the surface of the earth. Which takes place on the surface of the earth. And this will cause maximum destruction. And this will cause maximum destruction. And this will cause maximum destruction. Second one, Rayleigh wave. Second one, Rayleigh wave. Second one, Rayleigh wave. That's right. The up and down rolling motion. The up and down rolling motion vertically. The up and down rolling motion vertically can be seen due to Rayleigh wave. Can be seen due to Rayleigh wave. Can be seen due to Rayleigh wave. Okay. Put a sign, right? Surface destruction of property and life occur. Destruction of property and life occur. Destruction of property and life occur. Due to surface wave. Due to surface wave. Okay, no? Right. Done. Now let's talk about tsunami wave. Let's talk about tsunami waves. Clear? Now, in a tsunami wave or tsunami wave occur, a tsunami wave occurs mainly due to three main occurrences. First one is earthquake, which cause vertical movement of the tectonic plate. Vertical movement of tectonic plate. Vertical movement of tectonic plate. Next one. Asteroid hitting the sea. They say dinosaurs disappeared because of this. Third one, large iceberg crashing into sea. Crashing into sea and lake. Crashing into sea and lake. So these are the three main reasons why tsunami waves takes place. Now tsunami is also known as the harbor wave. What wave? Harbor wave. This is very common in Japan. This is very common in Japan, even though it's very rare for us, and we just had one experience in 2004. Tsunami waves are very common in Japan because Japan is in the region called Ring of Fire. Ring of Fire means there are so many volcanoes. There are more volcanoes under the ocean than above the ocean. So the Japan is there in a region called Ring of Fire. Is it clear? Highly tectonic, high tectonic, disturbances take place. So now these are the three reasons. Now the 2004 tsunami occurs. Now these are your tectonic plate. This is one tectonic plate. This is one tectonic plate. When they rub on it, they're trying to push each other. They're trying to push each other. Then one fellow says, jumps over each other. When jumps over each other, it will push the water above it. I told you, no. What did I tell you earlier? I told you, assume tectonic plates are floating on what? Tell me. Tectonic plates are floating on what? Quickly tell. Tectonic plates are floating on what? Which one? Very good. Lava. Tectonic plates are floating on lava, right? Above lava, what is happening? Above lava, what do you have? Above lava, you have water. Above lava, you have water. Above lava, you have water. Now imagine one of these plates push upwards. The water column here will push upwards. Water column here will push upwards. Understood? So when the tectonic plate shifts upwards, it will push the water in the upward direction. Once it pushes the water in the upward direction, what happens is gravitational potential energy of water will what? Increase. When gravitational potential energy of water increases, then it converts to what? Kinetic energy. And the wave will travel towards the earth. Because it has a lot of energy, it will go into the land, knock on trees, buildings, and then only what reduces its energy and becomes what? Zero. Is it clear? So the tectonic plate movement will push the water upwards. Now asteroid also same. Large asteroid will come and crash onto the earth, pushing the water where? Upwards. Iceberg falls on water, pushing the water where? Upwards. Creating what? A tsunami wave. Let's write it. Tsunami waves are also known as harbor waves. Tsunami waves are also known as harbor waves. Tsunami waves are also known as harbor waves. And they mainly occur. Due to the following three cases. Due to the following three cases. They mainly occur due to the following three cases. All right, first one. Earthquakes which cause vertical movement of tectonic plate. Example, 2004 tsunami. Asteroid hitting the water. So these what they assume how the dinosaurs went extinct. And then large iceberg crashing on water. Write these three quickly. Okay. Right? Done. Okay. Now remember when a tsunami takes place in the middle of the ocean, people in the ocean will not feel it. Even the 2004 tsunami, the fishermen who were in deep sea never felt it. The reason is very simple. Look at this very carefully. The tsunami wave deep sea right. Look at the board carefully. Now, when a tsunami wave occurs, velocity of the tsunami wave is defined as square root GD. Square root GD. Where D is the depth of the wave. Where D is the depth. Clear? So when a tectonic plate shifts upwards, when there is upward shifting of the tectonic plate, what happens is depth increases, velocity increases, kinetic energy will increase. Law of conservation of energy, no? Kinetic energy will increase. Clear? Now when kinetic energy increases, what will happen? Height of water increases and then converts to what? Gravitational potential energy. So here water is pushed upwards. So what happens is water is pushed upwards. Water is pushed upwards. Water is pushed upwards. When water is pushed upwards, gravitational potential energy increases. And because of larger depth, kinetic energy will also increase. Velocity increases, kinetic energy also will increase. And remember, this wave travels on the surface, so there is little, it's not touching the bottom of the ocean. So there is less loss of energy, no friction. Less loss of energy, no friction. And as the wave comes towards the earth, what happens? Height will reduce. Height will reduce. When height reduces, when height reduces, so as it gets closer, here depth is reducing, velocity reducing, kinetic energy reducing. What will increase? Gravitational potential energy will what? Increase. That is why when a tsunami wave is coming closer to the earth, height of the wave gradually starts what? To increase. And as it comes to the earth, the energy is so much it can't stop. Because it can't stop, what happens? It will travel to the land, hit on buildings, trees. So I'll show it like this. I'll show it like this, right? So here you have houses, you have buildings, you have trees, all of that gone. Tsunami waves will just travel inside because the energy is very, very large. So what's the energy conversion? Tectonic plate will shift upwards. Water increases in gravitational potential energy. Water is pushed upwards, increases in gravitational potential energy. The increased gravitational potential energy will convert to what? Kinetic energy. So greater depth, traveling very fast in deep sea. As it's coming closer, when it gets closer to the earth, what will happen? Depth will reduce, velocity will reduce, kinetic energy will reduce, gravitational potential energy will what? Increase. Then what will happen? The energy is still there. It will travel inside, knock on buildings, knock on trees, reduce its energy, and then what? Come the rest. Understood? That is why tsunamis are what? Very, very destructive. That's right. When a tsunami occurs, due to the vertical shifting of the gravity of the water, due to the vertical shifting of water, the gravitational potential energy of water will increase. The gravitational potential energy of water will increase. The gravitational potential energy of water will increase. And this will convert to kinetic energy. And this will convert to kinetic energy. And this will convert to kinetic energy. In deep sea, the kinetic energy will be large. In deep sea, the kinetic energy will be large. In deep sea, the kinetic energy will be large. But as it gets closer to land, as it gets closer to land, the depth will reduce, the depth will reduce, the depth will reduce, causing the kinetic energy to reduce, causing the kinetic energy to reduce, causing the kinetic energy to reduce. And this causes the gravitational potential energy of water to increase. And this causes the gravitational potential energy of water to increase. This causes the gravitational potential energy of water to increase. Gravitational potential energy of water to increase. And the wave will not stop near the seashore. And the wave will not stop near the seashore. The wave will not stop near the seashore. Because it has a large amount of energy. Because it has a large amount of energy. Because it has a large amount of energy. It will travel inland. It will travel inland. It will travel inland. Knock on buildings, trees. Knock on buildings and trees. Loses its energy and come to rest. Knocks on buildings and trees. Loses its energy and come to rest. Loses its energy and come to rest. I think you should draw this. It gives a nice indication exactly what happens when a tsunami occurs. This is speed of a tsunami wave. Speed of a tsunami wave. Draw below. So we have finished the tsunami wave part. Huh? So seismic waves over, tsunami waves over. Right. Right, finished. We can quickly go and look at a video. Okay. Finished, no? Are you done? Right. Right.
From above, the planet appears eerily.
Can you all hear it? Put a yes or no quickly.
Is a scar with many telling a story of when the Earth rumbled to life. Earthquakes occur around the world. They've been recorded on all 7 continents, but most quakes take place in just 3 regions. The Mid-Atlantic Ridge, an underwater line that runs down the Atlantic Ocean, the Alpine Belt, which stretches from the Mediterranean to Southeast Asia, and the Circum-Pacific Belt, which traces along the edges of the Pacific Ocean and is where about 80% of all earthquakes occur. These areas experience the most earthquakes due to what lies beneath the surface. Earthquakes are the result of pressure, specifically pressure caused by extreme stress in the Earth's crust. That stress can be caused by volcanic activity or even man-made activities in certain areas. However, most earthquake-inducing stress is caused by the movement of tectonic plates. Tectonic plates are constantly moving either against, away, along, or underneath each other. But sometimes their edges may catch and stick. The plates, however, continue to move, or at least attempt to. Energy from this attempted movement builds around the edge's sticking point, creating immense pressure until the edges are forced to let go and the plates slip. This causes a sudden and powerful release of energy, so powerful that it breaks the Earth's crust. This fracturing emits shock waves through the ground and causes intense vibrations, or quakes. In fact, the world's most earthquake-prone regions are where the most geologically active plates meet. Earthquakes, or any seismic activity, are recorded by seismographs. When the ground shakes, seismographs oscillate, drawing a jagged line to reflect this movement. The more extreme the earthquake, the greater the height of the jagged line. These recorded motions are then used to measure the earthquake's strength, or magnitude. While several scales of magnitude exist, the one seismologists prefer is the moment magnitude scale. It has no upper limit, and it measures earthquakes logarithmically. This means that each magnitude on its scale is 10 times greater than the one before it. Unlike the now rarely used Richter scale, the moment magnitude scale can be applied globally and can measure quakes of the highest magnitude. The largest recorded earthquake occurred near Valdivia, Chile in 1960. Nestled within the Circum-Pacific Belt, the Valdivia earthquake was the most powerful in a series of quakes that struck the region, measuring at a magnitude of about 9.5. In addition to causing devastating tremors on land, the earthquake also generated a deadly tsunami reaching up to 80 feet high. The tsunami raced across the Pacific Ocean, hitting faraway countries like the Philippines and Japan. In fact, data from seismographs show that the shock waves emitted by the Valdivia earthquake continued to shake the entire planet for days. Some earthquake-prone areas have adapted various ways to protect their communities. Buildings and bridges are designed to sway rather than break when an earthquake occurs. The public is educated on how to protect themselves during a seismic event, and government officials enact drills to ensure the protection of their people. Earthquakes can leave behind incredible devastation. But these same forces have also created magnificent features, with each adding character to a planet so unique.
Right. So this is about tsunamis. Huh?
16,000 lives. But the deadliest tsunami in history is believed to be the Indian Ocean tsunami of 2004. The U.S. Geological Survey estimated that tsunami released the energy equivalent of 23,000 Hiroshima type atomic bombs. An earthquake created an estimated 600-mile rupture on the ocean floor. This caused the tsunami to form and then travel at the speed of a jetliner, reaching over 11 countries, traveling over 3,000 miles, killing more than 220,000 people. Because they can strike so quickly with such deadly force, tsunami warning centers around the globe are on constant alert, monitoring underwater earthquakes large enough to trigger massive waves. Their ultimate goal is to alert vulnerable coastlines and give residents time to seek higher ground before a tsunami hits.
Right.
Movies have some of the most breathtaking sceneries you've ever seen.
Okay. Right. So you saw the video on earthquakes and also what tsunami waves, right? Tsunami waves. Right. Moving on. Next we can go into sonic boom. What is this? Sonic boom. So just another sound check. Can you all hear me clearly before we move on? Can you all hear me right now? Okay. Now, carefully listen. We know Doppler effect. So when a source is at rest, sound waves travel uniformly in all directions. Sound waves travel uniformly in all directions. So the gap between them is always equal. Huh? Gap between them is always equal. Here also lambda. Here also same lambda. You can keep a protractor and nicely draw this. Right. Source at rest. Now what happens is when the source starts to move, in one direction, have a look. The wavelengths in front will get close. All of you all know why? Frequency increases. Apparent wavelength you learn. And the wavelengths behind will start to increase. The wavelengths behind will start to increase, right? No? So when the source is going here, in front frequency is higher, so apparent wavelength is smaller. Behind frequency is lower, therefore apparent wavelength is large. So this is when the source is moving forward. Clear? This is when the source is moving forward. Next one, when the source is traveling at the speed of sound. Now here, source is traveling lesser than the speed of sound. This is speed of source. Speed of source. This is speed of sound. speed of sound. Here, if the source travels with the speed of sound, what will happen? Always the source will be in line with the front of the wave. Wherever the front of the wave is there, when the sound is traveling, the source is also there. When the sound is traveling, the source is also there. Every time the sound wave goes, source is there. So the source is exactly in front of the sound wave. Source is exactly in front of the sound wave. There. Now what happens is something very interesting happens. If the source travels greater than the speed of sound, velocity of the source is greater than the velocity of sound, what happens is a pressure cone is created. A pressure cone is created. You call this a pressure cone. A pressure cone is created. Now, when a pressure cone is created, look at this carefully. Properly draw the circle. Huh? There you go. Sound wave emitted here. Sound wave emitted here. Sound wave emitted here. There you go. This is called a pressure cone. This is called a pressure cone. Clear? This is called a pressure cone. Source is there in front, traveling. So a pressure cone is created. So the sound wave emitted here, perpendicular. Sound wave emitted here. So when the source emits a sound wave here, once it reaches there only, it has come here. So the sound wave emitted here, once the source reaches there only, has come here. The sound wave emitted here, understood? Sound wave emitted here, once the source is there only, reaches this edge. Sound wave emitted here, once it reaches here only, the sound, when the source has gone there only, the sound wave will reach here. Again, I'll explain. When a sound wave is emitted here by the source, when the source reaches there, the sound wave has come here. Sound wave emitted here. When the source has reached there, the sound wave has come here. Sound wave emitted here. When the source has reached there, the sound wave has come here. Sound wave emitted from here. When the source reaches there, the sound wave has reached here. So here you have a pressure cone. Here you have a pressure cone. Okay. And this is called, this angle here, I hope you can see it. I'll mark in black. This angle theta there is called half angle of the pressure cone. Half angle of the pressure cone. Half angle of the pressure cone. Okay. So here you have your symmetrical line. Here you have your symmetrical line. Half angle of the pressure cone is marked here. Half angle of the pressure cone is marked here. Half angle of the pressure cone is marked here. There you go. You know? So this angle here, that is called half angle of the pressure cone. Okay, half angle of the pressure cone. Okay, now right. I'll just there you go. So what do you learn from this? When the source is at rest, sound wave travels in all directions with equal wavelength. When the source is moving in one direction, in the direction it moves, the wavelength will reduce. Opposite to it, the wavelength will increase. Here, if the sound source is traveling at the speed of sound, if the source is traveling at the speed of sound, wherever the source, the front of the wave is, the source will be there. So the sound wave, wherever the sound wave is in front, the source is also there. Here, if the velocity of the source is greater than the velocity of the sound, pressure cone is created. And the pressure cone can be represented like this. You know? That's right. Consider the following diagram. Consider the following diagram. Consider the following diagram. When the source is at rest, when the source is at rest, when the source is at rest, the sound wave will travel in all directions in concentric circles. The sound wave will travel in all directions in concentric circles. Sound wave will travel in all directions in concentric circles. Next point. When the source travels in one direction, when the source travels in one direction, when the source travels in one direction, the wavelength in front will reduce while the wavelength behind will increase. The wavelength in front will reduce while the wavelength behind will increase. While the wavelength behind will increase. Next point. If the source travels at the speed of sound, if the source travels at the speed of sound, if the source travels at the speed of the source is always at the wavefront. The source will always be there at the front of the wavefront. The source will always be there at the front of the wavefront. Next point. If the velocity of the source is greater than the velocity of sound, if the velocity of the source is greater than the velocity of the sound, if the velocity of the source is greater than the velocity of the sound, a pressure cone is created. A pressure cone is created. A pressure cone is created. Okay, draw. Draw these two quickly, then we can draw the rest. Quickly draw. Right? Quickly work. right? Quickly draw. Carefully draw this, huh? Carefully draw this. Once you finish, quickly tell. Don't take a lot of time. The idea here is sound wave emitted here. When the wave reaches this edge tangentially, the source is here. When the sound wave emitted here reaches here tangentially, the source is there. When the sound wave emitted here reaches here, the source has gone there. So drawing all the circles inside that pathway, you call that what? A pressure cone. Have you all finished? Anybody finished? Answer in the chat quickly. Right. Okay. Now, what on earth is sonic boom? What do you mean by sonic boom? Now, when do you hear sonic boom? Sonic boom is heard when a jet travels overhead. Yeah. Sonic boom is heard when a jet travels overhead. Right. First, we'll go and listen what a sonic boom is. Let's listen what a sonic boom is. Right. This is a Sonic cartoon, no? Wait. Sonic Boom. Right. Now, when a jet travels, there is a katas, breaking noise. No? There's like a small breaking noise. That breaking noise is called what? Sonic boom. Okay? Carefully listen, okay? So it's building on speed. What I'll do is we can watch what do you call, I will watch it quickly. It's a long video. No? The Sonic Boom. I think from one of the shots we can see it. Okay, you will see some interesting shots. Huh? Watch. Huh? Yeah. Can you see the katas noise?
Reach the ground, they create a loud, explosive sound. As the jet travels faster and faster, the pressure waves can't get out of the way of each other. They build up and are compressed together. Eventually, they will form a single shock wave at the speed of sound. It can be heard from tens of miles away, depending on the size and shape of the aircraft. The pilot does not hear their own sonic boom. This is because the pilot is traveling supersonic, so the sound waves are unable to catch up with the jet. Sonic booms are often seen together with a cone-shaped cloud behind the aircraft.
Without explanation, we'll see. Watch, watch. Can you hear the explosion noise? Again, watch. The explosion noise, huh? So you can see, you will see like a cloud also form. Cloud also form. Can you hear? We'll watch one more. This very wonderful, huh? That pressure cone shape is there. There you go, the explosion. So you can see the pressure cone. Now you call this the shock egg or the shock collar. Here, no? Right. Now I hope you all saw the jet travel. I hope you all heard a cracking noise. And I hope you all saw like a cloud-like formation. How many of you saw this? How many of you heard the noise? You can type there. Heard the noise, saw the cloud. Heard the noise, saw the cloud. Quickly type. How many of you all heard the noise, saw the cloud? Come on, quickly, quickly. Done, no? Right. How many of you all heard the noise? Yes, you all heard the noise, right? The cracking, the kharas noise, the cracking noise, and the cloud-like formation. Saw the cloud. Did you all hear the noise? The cracking noise. Saw the cloud and heard the noise. Right, very good. Right. Now, how does this take place? Remember, only when a source travels beyond the speed of sound, goes supersonic. So the ones who said saw the cloud, didn't you all hear the sound? Huh? Didn't you all hear the sound? Okay, maybe we'll play it one more time later. Saw the cloud. Didn't you all hear the noise? The cracking noise? Hear or did not hear? Huh? Did not hear. Only. Okay, one more time. Let's see you. Because I want you all to. Okay, here we go. Listen carefully. Didn't you all hear this explosion noise? Didn't you hear this explosion noise? Did not? There's an explosion noise. Again, look. There we go. Now see it. When the rocket comes down. Now look. That one also.
There's final burn 1 and 2. 2 candles coming down. There they are. Double sonic booms.
The Tesla rocket. Now when the Tesla rockets come down, check and see the two explosions.
There's final burn 1 and 2. 2 candles coming down. There they are. Double sonic booms.
Heard? Lesser than the threshold of hearing. So these are the Tesla rockets. When the Tesla rockets are coming down, you'll hear double, what do you call, boom. Okay. So you can watch through these videos, just check and see. You will get to hear this noise. Maybe because of your some connection issue or internet, you can't hear it. Anyway, right? So there will be this cracking noise. Huh? There will be this cracking noise. Right. Now, how does this cracking noise take place? Look at the board carefully. Now, let's say a jet is traveling at supersonic speed. Supersonic speed means greater than the speed of sound. Huh? Supersonic speed means greater than the speed of sound. Velocity of the source. Now, when you're underneath the jet, you can't hear the sonic boom. When you're underneath the jet, you can't hear the sonic boom. Why is that? The sound wave emitted here will take some time to reach the ground. And when it reaches the ground, the jet has already gone forward. Jet has already gone what? Forward. So the sound emitted here, when it reaches the ground, the jet has gone forward, and the person just enters the pressure cone. When you just enter the pressure cone only, you can hear it. This person can hear. If you are outside the pressure cone, you can't hear. So this person can hear. Why can he hear? He is inside the pressure cone. This is the half angle of the pressure cone. This person cannot hear. Cannot hear. Why? Because he is outside the pressure cone. Now, what do you mean by this pressure cone? What do you mean by this sonic boom? Very simple. When the jet is traveling at supersonic speed, air particles near the nose. Now, the jet is traveling at very high speed. Air particles will come closer near the nose. Air particles will come closer near the nose. Okay? When air particles are closer near the nose, the pressure is high near the nose. The pressure is high near the nose. But when the jet travels very fast, the air will separate. The air will separate. And because it's traveling very fast, quickly it can't come behind. It can't meet. So behind here, the air is not there. There is less air. Less air means less pressure. Less air means less pressure. So there is a pressure drop. So there is a pressure drop. So here there is pressure. Maybe this is atmospheric pressure. Near the nose of the jet. This is the tail of the jet. Near the nose of the jet, the pressure is very high. Nose of the jet, pressure is very high. And because air separates, it doesn't come back quickly. So less pressure behind. To fill this pressure difference, there's a pressure drop, no? Air from the surroundings. Here high pressure. Here high pressure. Here low pressure. What happens is, to fill this low pressure from the surroundings, air will rush inside. From the surroundings, air will rush inside. Air rushes inside. When air rushes inside, the air particles will knock on each other. When they knock on each other, there's a cracking noise. Understood? That cracking noise is called sonic boom. Okay? So here, when the jet is traveling very fast, near the nose, the pressure is high, it separates. The jet is traveling so fast, it can't meet here, low pressure. Low pressure here than the surroundings. From the surroundings, air will rush inside in all directions. When air rushes inside, the air particles will collide, creating what? A cracking noise. That cracking noise is called what? Sonic boom. So wherever the jet goes, that cracking noise is going. Sometimes, until now, some of you all were thinking that is the sound of the jet engine. That is not the sound of the jet engine. Jet engine is far away. You can't hear the sound of the jet engine. You are hearing what? The sonic boom. Is it clear? You are hearing the sonic boom. Clear? You are hearing the sonic boom. So understood? Did you understand how sonic boom takes place? Clear? Did you understand how sonic boom takes place? When you are traveling at very high speed, the pressure in front, air particles are very close here, they separate, less pressure here. From the surroundings, air will rush in, creating what? A cracking noise. Why do you have the cracking noise? Sound will what? Air particles will knock on each other, Friction will create what? A loud noise. And that is called sonic boom. Okay, no? That's right. That's right. When the jet is traveling at supersonic speed, when the jet is traveling at supersonic speed, when the jet is traveling at supersonic speed, the pressure near the nose, the pressure near the nose, pressure near the nose will be very high. The pressure near the nose will be very high compared to the tail of the jet. 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 Since the pressure drops suddenly, since the pressure drops suddenly, since the pressure drops suddenly from the surroundings, from the surrounding, from the surrounding, air will rush in to fill the low pressure. Air will rush in to fill the low pressure. Air will rush in to fill the low pressure. Air will rush in to fill the low pressure. And as air rushes in, the air particles will collide with each other. The air particles will collide with each other, creating a cracking sound. Creating a cracking sound. Creating a cracking sound. This cracking sound is called the sonic boom. This cracking sound is called the sonic boom. This cracking sound is called the sonic boom. The cracking sound is called the sonic boom. And wherever the jet travels, this sound will follow the jet. And wherever the jet travels, this sound will follow the jet. Wherever the jet travels, this sound will follow the jet. Right. Next time, right? When the jet is above the man's head, the person cannot hear the sonic boom. When the jet is above the man's head, the person cannot hear the sonic boom. The person cannot hear the sonic boom. Only when he enters the pressure cone. Only when he enters the pressure cone. Only when he enters the pressure cone, the sonic boom can be heard. The sonic boom can be heard. The sonic boom can be heard. Okay, draw. right? Okay. Now, I'm going to teach you how to calculate these things. Have a look. Now, what do you mean by this pressure code? I told you. I'll take a few locations. Here you go, the pressure code. The sound wave emitted here, when it reaches here, the jet is here. The sound wave emitted here, when it reaches this way, the jet has reached that place. I will take this one circle and explain it easier. This is half angle of a pressure cone. Half angle of a pressure cone. What is traveling here? Here who is traveling? Source is traveling. So time taken for the sound wave to come here and time taken for the jet to go there, both are what? Same. So I'm using only one sonic boom here. Easy for me to explain. T equal naught, time taken for the sound wave to come here and time taken for the jet to go there, both are what? Same. Here T equal naught. If you look at this carefully, sin theta is opposite over hypotenuse. Here 90, no? Opposite is going to be this. Opposite over hypotenuse. Opposite is going to be this length. That is going to be velocity of sound into time. Hypotenuse is here. That is equal to Vs into T. T cancel off. Sin theta is equal to V over Vs. Now be careful. Sin theta I can write 1 divided by Vs over V. What is Vs over V? Velocity of source divided by velocity of sound. How fast is the source going with respect to sound? We define the Mach number. Mach number is defined as Mach 1, Mach 2, Mach 3 like that. Velocity of the source divided by velocity of sound. Mach 2 means double the velocity of sound. Mach 3 means 3 times the velocity of sound. So I can substitute here sin theta is equal to 1 over Mach number. Sin theta is equal to 1 over Mach number. Here you go. A very important relationship when you solve sonic boom problem. This is also important relationship. Since I have defined this earlier, I won't define it now. Vs is velocity of the source. Here I have defined it here. No? I have defined it here. Speed of the source, speed of sound. Here I have defined it here. Since I have defined it here, I will not tell it again. So here you go. Half angle of the pressure cone and the Mach number can be represented like this. Okay, that's right. As shown in the figure, when the sound wave emitted at O, when the sonic boom emitted at O, reaches A, when the sonic boom emitted at O reaches A, the jet has traveled to B. The jet has traveled to B. The jet has traveled to B. Not down, perpendicular. Okay. From this, we can find the following relationship. From this, we can find the following relationship. From this, we can find the following relationships. Quickly draw, work it out. Right? Done? Okay. Write the following example. Vilu. Write the following example. Right. Write the following example. A jet travels with Mach 2. A jet travels with Mach 2. Find the half angle of the pressure cone. Find the half angle of the pressure cone. Find the half angle of the pressure cone. Keep about 2 or 3 lines. Next one. A bullet travels through nitrogen gas. A bullet travels through nitrogen gas with a velocity 418 meters per second. With a velocity 418 meters per second. Where the half angle of the pressure cone is 53 degrees. Where the half angle of the pressure cone is 53 degrees. Find the velocity of sound in nitrogen gas. Find the velocity of sound in nitrogen gas. Find the velocity of sound in nitrogen gas. Do those two quickly, will quickly work. So very simple problems they will ask. Right, no? So half angle of the pressure cone is given, Mach number is 2. Sin theta is equal to 1 over 2. Sin is equal to 1 over 2. 1 over 2 means sin theta. Theta is equal to how much? 30. Half angle of the pressure cone is 30. Okay? Half angle of the pressure cone is 30. Next is speed of the source over speed of sound. Half angle of the pressure cone is given. So I'll erase this and do. One over Mach number, sin 53, velocity of the bullet 418 divided by velocity of sound in air in the bullet. V goes on top. Sin 53, V divided by 418 cross multiply. 418 multiplied by sin 53. 418 multiplied by sin 53 will give you the answer 333.8. 333.8 meters per second. That is the velocity of sound in nitrogen gas. Clear? Understood? So this is not difficult. Right. Okay. Right. Write the third and final example. Third and final example. A jet is traveling at 20,000 meters above the ground. A jet is traveling at 20,000 meters above the ground. A jet is traveling at 20,000 meters above the ground. At Mach 3. At Mach 3. Speed of sound in air is 335 meters per second. Speed of sound in air is 335 meters per second. 335 meters per second. Right. Roman number 1. How long does the shock wave emitted above the head of the person? How long does the shock of the pressure wave emitted above the head of the person? The shock of the pressure wave emitted above the head of the person take to reach the person? Take to reach the person. Take to reach the person. Keep some space, Roman 2. When the person hears it, how far has the jet traveled? How far has the jet traveled? How far has the jet traveled? Right. Now remember, these are two separate ideas, two separate problems. Carefully think. Now what are they telling you here? What's the main theory? Sonic boom emitted here will take a time simple t this way, not that way, this way. Same time the jet has gone forward. Look at the board now. Jet is above the person's head. When will he hear the sonic boom? He will hear the sonic boom when the jet has traveled forward like this. When this flow just enters the pressure cone. just enters the pressure code. Now, what's the definition? Time taken to go here perpendicularly. Here perpendicularly. Time taken to go here perpendicularly and time taken here both are what? Same. This time and this time are not equal. This time is how high the jet is traveling. 20,000 meters. Is this clear? Is this clear? You can clearly see, this distance and that distance, are they same or different? Obviously different. This is much more longer. Time taken from here to here and time taken from there to there are same by definition. Understood? Clear? No? Right. First question is, so don't mix these two. These something separate. So the sonic boom emitted here will travel from that line and reach the person. So time taken here, distance is 20,000 divided by speed 335. 20,000 divided by 335. Yeah. 20,000 divided by 335. You will get your answer 59.7. 59.7 seconds. Now tell me, time taken for the sound wave to go here 59.7 seconds. Is it the same time to go there? No. Time from here to here and time from there to there are same. But this time and that time are not different. So how do you find the distance traveled by the jet? Distance traveled by the jet is geometry. Horizontal, vertical, 90 here. If they ask you to find that, find it, but they have not asked you to find it. Then how will you solve this? Sin theta or tan theta, sorry. Tan theta, opposite to adjacent. Opposite to adjacent. All of you all know sin theta, mark 3. In the problem they are given you, it's mark 3. 1 over mark number 3. So sin theta is this. Look at the board. If sin theta is this, you must substitute for tan theta. Sin theta is opposite to hypotenuse. 9 minus 1 is 8. 9 minus 1 is 8. Now what is tan theta? Tan theta is opposite to adjacent. 1 over root 8. 20,000 divided by x. Cross multiply. X is 20,000 into square root 8. 20,000 into square root 8 meters. 20,000 into square root 8 meters will give you an answer. $56,600 meters. That's about 56.6 kilometers. Understood? No? Time taken here and here are same, but time taken here and here are not equal. Don't confuse. So from this right angle triangle, you can see the 90 degree. Opposite to adjacent tan theta, also sin theta is 1 over mark number. From this right angle triangle, you can get the answer here. You can get the answer there. Okay, no? So this don't forget, time taken from here to here is same as the time taken from here to here. But time taken here this way, that time and that time are not equal. Okay, no? Clear? Write down carefully. So right, sonic boom also done. So we are done tsunami waves, seismic waves, we are done sonic boom. Right. Finally, laser. Now the laser theory we'll do it here. And whenever we meet in class, we'll do what questions, because I don't think we'll have time for questions, but we will be able to have time to what finish the concept of laser. Right. What is laser stand for? So laser stands for light amplification by stimulated emission. Stimulated emission of radiation. Stimulated emission of radiation. They have taken the first letters and found this. Light amplification by stimulated emission of radiation. Write the topic. Light amplification by stimulated emission of radiation. Right. Now, a bit of chemistry work. There's a lower level. We'll call it E0. Here there's a higher level. So what happens? Electrons are there in the lower level. Electrons are there in the lower level. So when energy is given, these electrons gain energy and go to a high energy level. These electrons gain energy and go to a high energy level. You call this process absorption. You call this process absorption. But at the higher energy level, they are very unstable. At the higher energy level, they become very unstable. When they become unstable, tell me what happens. When they become unstable, what will happen? They will emit energy and move to the ground. They will emit energy and move to the ground. Now, when you emit energy, energy is emitted in the form of photons. These photons travel in all directions randomly. These photons travel in all directions randomly. Energy of the photon is HF. Energy is the energy difference between the levels E1 minus E0, that is equal to HF. Now you can see this part is called spontaneous emission. This part is called spontaneous emission. Spontaneous emission. And look at these properties. Spontaneous emission. The photons are traveling in all directions. It is not directional. It doesn't have the same phase difference. They're not directional. Doesn't have the same phase difference. Doesn't have the same intensity. That is called what? Spontaneous emission. This is what you learn in chemistry. Electrons gain energy, go to a high energy level. They become unstable there. Thereby, photoelectric effect, they will drop to low energy levels, emitting what? Photons. And these photons are called what? Due to spontaneous emission. So what are the drawbacks of spontaneous emission? First one, no direction, non-directional, no direction. Next is less intensity. Why? When they are not going together, the intensity will be less intensity. So non-directional, less intensity, Phase is not constant. Phase will keep on what? Changing. Here, phase will keep on changing. So what do you call this? Spontaneous emission. Now what is laser? This spontaneous emission is the light coming from a fluorescent bulb. That is because of what? Spontaneous emission. Here, that is because of spontaneous emission. Now what do you mean by stimulated emission? Stimulated. Here ground energy level, first energy level, second energy level. All of you all know, no? As the energy levels increase, the gap between them will what? Reduce. Right. So what happens? Absorption time. Electrons gain energy and go to a higher energy level. High energy level. This is called absorption. This is called absorption. Then what will happen? Then what will happen? E0, E1, E2. Now electrons are here. Now what happens? They drop down to a lower energy state with no radiation energy emitted. No radiation energy emitted. No radiation emitted. Now you might wonder, sir, can this take place? High energy level to low energy level, we have learned in chemistry that there is energy emitted. No. There is a special state when it drops. No energy is emitted. That special state is called metastable state. Metastable state. So electrons gain energy, go to a high energy level. They drop to a metastable state. They drop to a metastable state. Now, part of having what we call this process is having more electrons. More electrons means we give more energy here. More energy by absorption due to heat or sound or electricity. Electrons move to a high energy level, they drop toward the metastable state. Now, what happens? At the metastable state, electrons are now here. What happens? An incident photon comes with the same energy, E1 minus E0. When the incident photon comes with the same energy, it will knock these electrons to the ground energy level. It will knock these electrons to the ground energy level. Right. This is called stimulated emission. This is called stimulated emission. I'll give a small example like this. Look. When you are in school, when the interval bell rings, or when the assembly bell rings, or early morning bell rings, what happens? Most probably interval bell or after school bell. After school bell rings, the smaller grade fellows will run in all directions. If you are a prefect, you know, it's very difficult to control the smaller fellows. That is same as what? Spontaneous emission. The children have no direction. One fellow is running in front, one fellow is running somewhere else, one fellow is climbing a tree, one fellow is licking sand, one fellow is rolling on the floor. high energy is focused in many directions. So it's non-directional. Less intensity because they are traveling in all directions. So travels in all directions, non-directional. Less intensity, so travels in all directions. Travels all directions. Travels all directions. And the phase is not constant. They are emitted at different times. Imagine laser light as taking that naughty child and sending it to an army camp or hostel. It will absorb energy, drop to this metastable state. When you are in the army, you must be like, you must absorb that subculture. You must do exactly whatever they tell you. So there is a subculture there. That's called what? Metastable state. When you are in school, your school has a subculture. You have to what? Adhere to that subculture. Likewise, universities, when you go, they have a subculture. You must what? Quickly adapt yourself to that subculture, then there is no problem. So these called metastable state. When you drop to that metastable state, you're not losing any energy, no radiation emitted. Then what happens? Just like the hostel warden, just like the army barracks commander, what happens? There is an incident photon having the same frequency difference. This incident photon will stimulate emission, and each photon is emitted. Look at this very carefully. Each photon is emitted. Each photon is emitted in the same direction. Each photon is emitted in the same direction, having the same energy difference. Having the same energy difference. And this light is what we call laser light. This light is what we call laser light. Laser light, you can see, is highly directional. Highly directional. High intense. High intense. All the photons are emitted at the same time, same phase. Same phase and same frequency. Same frequency. So what do you call this? Stimulated emission. We call this the laser step. We also call this the laser step. Right. When it reaches the ground level. So you can clearly see we can't do laser for two levels, two energy level system. Why? There should be a metastable state. So we can start doing this by a 3 energy level system laser. So 3 energy level laser. 3 energy level laser. There you go. Understood? Is it clear? So normally what happens? You absorb energy, go to a high energy state, unstable, you drop, you emit photon. That is called what? Spontaneous emission. Clear? Let's write. Let's write. When energy is given, electrons will absorb this energy and move to a higher energy state. Electrons will absorb this energy and move to a higher energy state. Electrons will absorb this energy and move to a higher energy state. But at this energy state, it is unstable. But at that energy state, it is unstable. So it will emit photons. So it will emit photon and drop to the low energy state. It will emit photon and drop to the low energy state. This is called spontaneous emission. This is called spontaneous emission. This is called spontaneous emission. Next time, right? The photons emitted by spontaneous emission, the photons emitted by spontaneous emission is non-directional, less intense, and the phase is not constant throughout. 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 Clear? If you have done chemistry, I think you have done this. But the IT one, low energy level, high energy level, high minus low difference, that is equal to H. So photons are emitted between these two energy bands. Draw it. So is it clear? So 20 more minutes, then we are done with the main theory. Yeah? So bear with for 20 more minutes, then you're okay. Understood this? So you can name this ground energy level. Ground level, E naught. So first energy level. First energy level. Okay. You are finished drawing, quickly say you are finished drawing. Clear? Right. Next time, right. For laser to occur, there should be stimulated emission of radiation. There should be stimulated emission of radiation. There should be stimulated emission of radiation. For this, we start with a 3 energy level system laser. We start with a 3 energy level system laser. We start with a 3 energy level system laser. That's right. Through absorption, electrons reach a high energy state. Through absorption, electrons reach a high energy state. Through absorption, electrons reach a high energy state. And then they drop to the metastable state. And then they drop to the metastable state. And then they drop to the metastable state without emission of radiation. Without emission of radiation. Very important. So when things fall to the metastable state, no radiation is emitted, guaranteed. Without emission of radiation. Without emission of radiation. And when it is at the metastable state, and when it is at the metastable state, an incident photon having the same energy, an incident photon having the same energy, will stimulate the electrons to drop from the metastable state, will stimulate the electrons to drop from the metastable state to the ground state, from the metastable state to the ground state, from the metastable state to the ground state, from the metastable state to the ground state. Emitting photon, emitting photon, emitting photon, which have the following properties. Which have the following properties. So the photons emitted here. Now remember, if you go to the army, imagine these are soldiers. Once the training period is over, the soldiers and the commander all are marching together. So these are the soldiers having the same energy difference. And remember the incident photon also. Incident photon also will travel in the same direction. I will mark that later. Let's say from the metastable state will drop to a low energy state, emitting laser light, emitting laser light, emitting laser light. Light. The laser light is what? Put Roman 1. Laser light is Roman 1. Highly directional. Highly directional. High intense. High intense. Highly directional. High intense. Has the same phase. We call this coherent as well. There's another word used for this. Coherent. 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 And has the same frequency. And has the same frequency. And has the same frequency. The emitted photon and the incident photon will travel together in the same direction as shown. The incident photon here, the incident photon and the emitted photons or laser photon will travel in the same direction as shown. So imagine army soldiers marching. Left means left, right means right, left means left, right means right. That means they are what? Moving in highly direct. Imagine a army parade. In an army parade, every single soldier, same action. Coherent. Highly directional. And because they are together doing the same thing, the intensity is very, very high. So the laser photons and the incident photons, they will travel in the same direction. So what do you call this? Stimulated emission. You know? Stimulated emission. Right. Draw. Quickly draw. You are finished. Quickly say done. Laser step. Incident photon will come, stimulate this, these will drop. Photons are emitted, incident also goes. All are traveling in the same. Imagine a commander leading the soldier. Commander leading the soldier. This is the laser. You are finished. Indicate you are done. Right. So what did you just learn now? 3 energy level system laser. Then you have 4 energy level system laser. 4 energy level system laser. So you have 4 energy level. I'll try to draw it here itself. E is here, E naught, E1, E2, E3. So here you have absorption. So what is absorption? Electrons at the lower level gain energy and reach the higher level. Then what will happen? They are unstable. They are unstable. What will happen? Electrons will drop from the higher energy state like this. But no radiation is emitted. No radiation emitted. No radiation emitted. No radiation emitted means, tell me, what do you call this state? Quickly tell. No radiation emitted means, what do you call that state? Type quickly. What do you call that state? Huh? What do you call that state? Metastable state. Very good. Metastable state. Metastable state. So no radiation emitted, metastable state. Then what happens? Look at the board. E0, E1, E2, E3. Electrons are there in the metastable state. Now what happens? This is your laser step, simulated emission. Incident photon comes having energy difference E2 minus E1. Incident photon comes. Incident photon comes. Energy difference E2 minus E1. E2 minus E1 will cause electrons to drop to the lower energy state. Electrons to drop to the lower energy state. But the beauty is, all photons emitted and the incident photon will go in front, just like soldiers marching, having the same energy difference. What? E2 minus E1. What do you call this? Stimulated emission. Stimulated emission. Right. Stimulated emission. Just to finish the picture here itself, then you have picture D. Picture D. E0, E1, E2, E3. Now the electrons are here. They drop to E1. They drop to E1. From here, quickly they will what? Drop to the ground level. Here was something beautiful. No radiation emitted. No radiation emitted. Because all the energy is emitted here. So what do you call this? You call this a 4 energy level system laser. 4 energy level system laser. No radiation emitted. Clear, no? Okay. All right. Four energy level system laser. Quickly draw. Once you finish, let me know quickly. So remember these sections I did today, I will not teach in class again. So sonic boom, tsunami waves, seismic waves, and laser. Questions we might solve in class, but whatever theory that is needed is completely taught and finished. It is also called the laser step. That's also called the laser step. It's a bit ugly. So here laser step. Laser step. So like this, you have different levels of laser. Okay. So red laser, green laser, blue laser, different colors you will have, but all of this fall under this. The same process is going to be the same. Basic process is always going to be what? Same. There is going to be stimulated emission. So A, B, C, then D. Yeah? If you are finished, let me know. Done. Right. Now tell me, finally, what are the applications of laser? Where do we use laser? Laser is used for what? Laser printers, printing technology. Laser is used for what else? Cutting technology. Cutting metals and all, laser is used. What else? Laser is used as what? A laser pointer device. Next, laser lights, disco lights, laser lights. So for entertainment, laser lights are used. What else laser lights is used for? Surgery. Eye surgeries are laser. Removing blackheads, laser. Then what you call some laser surgeries internally, all of that. So medical applications are there. Laser endoscopy also has laser on one end. So laser burning, laser cutting, all of that. Sensors. Sometimes in bank movies you have watched, laser lights are there. The moment you cut, alarm starts going on. Yeah. So it's used in a wide spectrum of applications. That's right. Laser is used. Laser is used in spectroscopy. Spectroscopy. Material processing. Material processing. Photochemistry. Photochemistry. Also now, when a gun, the distance is measured using what? Laser. Right there. To measure distances. To measure distances. Next. For eye surgery, endoscopy. For eye surgery, endoscopy. When you go to Keels and Cargills, what do you have? Barcode readers. Barcode readers use laser. Barcode readers use laser. Barcode readers. Laser printers. Laser printers. Next one. Laser lights and holography. Holograms, have you heard? By using 3 laser lights kept at different angles, you can make a particular shape like a real person talking. Hologram. Okay. So there you go. Those are your applications. Remember this laser step. Energy is emitted as a photon. This laser step, if I write it here, E2 minus E1 is equal to HF. You can go to the picture and write. Remember, photons travel at the speed of light. So C over lambda. That is E2 minus E1. The C is speed of light. C is speed of light. Quickly write it near 4-level laser. Quickly go and write it near 4-level laser. So next week we just have to substitute values for this and find answer. HC over lambda. C is speed of light. E2 minus E1 is the difference in the energy level in the laser step. Right, let me go back. 3 energy level system laser. Here. So what is your laser step? E1 minus E0. That is HF. E1 minus E0 is equal to HC over lambda. Write down, will write down. This is how the calculation is done. Okay, no? Right. That concludes this session. I hope it was very useful for you all. So I didn't want to actually, allow you to just stay on election day because most of you all would have been free at home today in the evening. So we utilized the time much more effectively. So therefore, I hope you look these very carefully next time before you come to class because you'll be solving some problems connected to this. So enjoy the rest of the day. I'll catch you all again in a session like this. I will let you all know in the groups. Maybe something else we'll be doing. Okay? Right. Take care. Keep studying.